Hi, welcome to AP Physics C. We've got a block projected up a frictionless incline. Our goal today is to use the conservation of mechanical energy to solve a problem involving gravitational potential energy, spring potential energy, and a ramp. Okay, so in this problem, we're going to have both types of potential energy. So the problem is that we've got a block here. It's at rest on a horizontal frictionless surface as in the figure. The block is pressed back against a spring having a spring constant of 625 newtons per meter. It's compressing the spring by 10 centimeters to point A, and then the block is released. Find the maximum distance d the block travels up the frictionless incline if theta is 30 degrees, and how fast is the block going when it's halfway to its maximum height. Okay, so we've got the block here. It's compressed 0.1 meters. It travels up this ramp here, and when it reaches its maximum height, it's at rest, right? And so what we're trying to find here is the distance d. That's part A. And then for part B, what we want to do is find out how fast it's moving when it's at a half of that height, half of that maximum height. All right, so here we go. Okay, so I've drawn that problem right here. I've written down all my givens. Okay, so I said that we're going to use the conservation of mechanical energy, but we don't know that we can actually use the conservation of mechanical energy. Remember, the condition is that the non-conservative forces have to do no work. Okay, so what you want to do is you want to draw a free body diagram in basically all phases of the trip. Okay, so I'm going to draw a free body diagram when it's along this ramp here. I'm along this horizontal surface. I'm going to draw a free body diagram over here along this inclined surface. So I've drawn my two free body diagrams, and I have to ask myself if the non-conservative forces, if they do any work, right? Because if they do work, then I cannot use the conservation of mechanical energy. Okay, well, weight and spring force, okay, when I have the block here, I have a spring force pushing the block to the right. We have our weight, we have our normal force. Okay, these are conservative forces, so I'm not worried about these conservative forces. I'm only worried about the non-conservative force. So the normal force here is non-conservative. So is it doing work? No, it's not doing any work because when it's moving to the right, the normal force is perpendicular to the displacement. Okay, so we're good so far. How about over here? Well, actually, that means we can definitely use conservation of mechanical energy on this part of the trip. What about that part of the trip? Okay, well, we have a normal force and we have the weight, right? The incline is frictionless, so no friction, and there's no spring force. Okay, so I have a conservative force. I don't check that one. I just check the non-conservative forces, which is the normal force here. And again, when it's on this part of the trip, the displacement is up that ramp and it's perpendicular to the normal force. So that means energy here is conserved, or mechanical energy is conserved this entire trip. So that means I can use the conservation of mechanical energy. Okay, so if non-conservative forces do no work, mechanical energy is conserved, which means the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. And actually, it's just anywhere you want, like anywhere along the whole trip. If you pick 2 points anywhere, not just the initial and final points, like the sum of the kinetic energy and the potential energy are the same. Okay, so part A wants us to find out what this distance is here. How long is this ramp? Okay, so what I'm going to do is I'm going to use the work energy theorem for this entire trip. I'm going to use it from point A. A is going to be my initial point, and C is going to be my final point. Okay, and so I basically just expanded all of this, right? Kinetic energy is 1/2 mva squared. Potential energy is both gravitational and spring potential or elastic potential. So we've got mgha for the gravitational, and then we've got 1/2 kx squared for the elastic potential energy. Same thing over here. Okay, now what I'm going to do is I'm going to ask myself, do any of these go to zero? Okay, a lot of them go to zero. This guy starts at rest, so that's zero, and then that whole term is zero, so we don't have to worry about this guy. The height is zero, right? If I call the ground level my zero position. Okay, so this guy is going to be zero. So this whole term goes to zero. I don't need to worry about him. We do have a compression, right? We're compressed 0.1 meters. So this one is something that's not zero. The velocity at c, right? They want the maximum height here, so it's at maximum when it's at rest, right? So this guy is actually 0 too. Okay, and then there is a height, right? We can see that it's risen above the ground, so we can't send that to zero. But over here, what is the spring? How far is it compressed? The spring is not even involved in this part of the problem. So we're not even worried. We don't have any elastic potential energy at C. Okay, so all we've got left is basically this guy here. We've got 1/2 kxa squared is equal to mghc. All right, what are we trying to find? We're trying to find D, right? And it looks like we're going to be able to solve for h. And then once we have h, and we know this angle here is 30, we can just use the sine, right? The sine of this angle is h over d. We'll just use a sine to solve for d. Okay, so hc, or the height at c, is just going to equal 1/2 kxa squared all over mg. And then I know that the sine of 30, that's going to equal h over d, right? So I know that d is going to equal h over sine 30. So I can just substitute all of this in. So this is going to be 1/2 kxa squared all over mg sine 30. Okay, sine 30 is just a half, so I can actually cancel that out. And so we've just got kxa squared divided by mg. And I'm going to just solve that right over here. So the distance is going to be k, which is 625. And then we've got x, which was 0.1. It was compressed 0.1 meters. Kx squared all over the mass, I believe, was 0.5. And 9.8 for gravity. Okay, so that d value is just going to be 1.28 meters. Hey guys, welcome to part B, where we're going to solve for the velocity at point B here. Okay, so we've already figured out that we can use the conservation of mechanical energy anywhere. Okay, and right here we have a different height, so we have a different gravitational potential energy, but it's just the same as this guy divided by 2. Okay, they defined that in the problem. They said, hey, find the velocity at when the height is half of the height at its maximum distance up the ramp. Okay, so I found out what that was. It's 65 over 196. I'm just using exact values. Okay, and I know I can use the work energy theorem, right? I'm sorry, the conservation of mechanical energy. So that just says that the mechanical energy at any point is equal to the mechanical energy at any other point. Okay, so we have two choices. We can choose point C, or we can choose point A, or you can choose any other point anywhere, but we know information about the block at A, and we know information about the block at C. Okay, so I'm going to choose to use the block or the position at point C. You could have chosen to use the position at point A. It doesn't matter because mechanical energy is conserved everywhere. Okay, so the kinetic energy at B, it definitely has kinetic energy because that's what we're trying to find. So that's 1/2 mvb squared. And then the potential energy at B, well, there's elastic potential energy and there's gravitational potential energy. There is no elastic potential energy over here because the spring is not involved in any any way. So we only have gravitational potential energy. So that's going to be mghb, okay, or the height at B, which is 1/2 h, right? But we're writing height B, height for B. Okay, so 1/2 mbc squared. It's actually at rest here, so I should just send this guy equal to 0, right? Plus the potential energy due to elasticity, right, or the spring, but there's no spring involved over here, so I don't have any of that. And then I have the gravitational potential energy, so mgh at C. Okay, so what I'm going to do here is I'm going to rearrange all of this. I'm going to substitute in some numbers, cross out these masses, right? The mass is involved in each one of these guys here. So then I just have the velocity at B squared times 1/2 plus g h over 2. Let's call it h over 2, right? Because h at B, the height at B is just the height at C divided by 2. And the height at C is called h. Okay, and then we're going to equal it to g. hc is just h. Okay, so now all I have to do is solve for VB. So VB is going to equal, this is going to be GH minus GH over 2. So I can factor out an H, right? Or yeah, GH. Can factor out a GH. So it's going to be 1 minus 1/2. Okay. All I did was subtract this term onto the other side and factor it out of GH. So I get 1 here minus 1/2. And then I get divided by 1/2. And then we take the square root of all of that. Okay, 1 minus 1/2, that's just 1/2. So these cancel out. So the velocity at B is just equal to the square root of GH. And how much was the height? Well, remember, it was equal to this in part A. And I figured out that that was 65 over 98. So the velocity at B is equal to 9.8 times. I already figured out what it was. It's 65. Actually, it's 65 over 98. H over 2 is 65 over 196. So, all right. And so the velocity at B is going to be, I figured out what it was, but I totally deleted it. So let me do it all over again in my calculator. 65 divided by 98 times 9.8. Square root of 6.5. So square root. So 2.54 or 2.55 meters per second. Okay, you could have done the same thing, but at point A, you could have written A's here. And in that case, you would have had no gravitational potential energy, no velocity because it's at rest, but you would have had the 1/2 kx squared. Okay, so sorry about that. You couldn't see that. That's up to you. All right, have a great day.